Hello, welcome back to three-phase circuit analysis. We're going to study this circuit. We're solving our problems here. I'm going to be the first to admit this problem's a nightmare. It's a mess. You know, all of them are. All of the three-phase circuits are, because they're going to have a lot of values running around. But ultimately, you have to take every little piece step by step, and you just kind of have to work through it. And when you do enough of them, then the diagram doesn't scare you so much because you know how to read it. So we have essentially three phases. We have a phase A, which is here. We have a phase B in the middle. And we have a phase C coming down below. We have a neutral terminal on the source side, lowercase n. We have a neutral terminal on the load side, uppercase n. And then every part of the circuit is sliced vertically like this. So you have the lowercase a, b, and c. Those nodes to the left denote the sources, right? So you have the voltage sources here, which are outlined, 240 angle 0, 240 angle 120, 240 angle negative 120. But then you have these impedances here all the way up until the lowercase a. This is the source impedance of this source, of the winding, basically. You have a resistance and an inductance associated with that source. Same thing with this source, same thing with this source. So even though, if you cover all this up, even though it still looks ugly when you read it like that and realize, well, this is an impedance for this is an impedance for this, and this is an impedance for this, it becomes a little more tractable. You understand why everything is there. Then we have the central part between the letters A, B, and C, and we have this impedance here. This is the line impedance. This could be a 100-mile long transmission line or a 10-foot long transmission line, whatever. You have a resistance and an inductance associated with that. Resistance, inductance, resistance, inductance, okay? And then off on the right-hand side, everything beyond the capital A, B, and C, that's always called the load. So this is going to be true of all of these problems. So this is the load. We have a load impedance here, resistance, inductance, resistance, inductance, resistance, and inductance. Now from the neutral terminal coming back all the way to the source, we have our neutral line. Now real circuits, real wires have some kind of resistance. So in this case, we're saying 10 ohms. Sometimes you might see an inductance here, whatever, depends on your problem. But in this case, we don't have any inductance in the return line. It's just a 10 ohm resistor. It's how it's modeled. So we have a source part of the circuit, a line part of the circuit, and a load part of the circuit, and it's a Y-Y configuration. You don't see any triangles or any delta configurations, it's Y-Y. So we have three parts. Number one, is this circuit a balanced three-phase circuit? Number two, what is the phase sequence associated with this circuit? Number three, what is the return current I sub 0, okay, or I naught? The first thing you need to be aware of is some of this stuff can be answered right away without any calculations. If this circuit is a balanced Y-Y circuit, and we know when we'll go through exactly what it takes to be balanced in a second, but if it's a balanced, then by definition from the lectures before, you should automatically know that if this circuit is balanced, then the return current I sub 0 is going to be 0. Because if the circuit's balanced, there's no current, no net current coming back. That means we can remove this conductor completely between the neutral terminals and throw it away, and it doesn't affect anything. Or we can replace it with a short circuit or whatever. It isn't going to be relevant if the circuit's balanced. So if this first question comes out to be yes, the circuit's balanced, then you automatically know without doing any calculations. You could, of course, verify with the math, but you don't have to verify anything, that you will know I naught is going to be 0. I just want to point that out. So when they ask you if it's balanced, and then they ask you what I naught is, then you might probably guess that it's probably not going to be a balanced circuit, because otherwise why would they even ask you what I naught is? All right, most of the circuits that we're going to study are going to always be balanced. Let's see if this circuit's balanced. So in order to be balanced, we have to first have a balanced three-phase set of voltages on the source side. So we have 240, those are the amplitudes, and we have 0, positive 120, and negative 120. So it looks like this is a balanced set, and we'll talk about what the phase sequence of that set is in just a second, but it looks at first glance to be a balanced set of voltages. Now, in order for the remainder of the circuit to be balanced, we have to have the source impedances all match. So 0.1 ohm, 0.1 ohm, 0.1 ohm, J.8 ohm, J.8 ohm, J.8 ohm. So the source impedances are all the same for all three sources, so that's good. Then the line impedances on all three phases have to be the same. 0.4, 0.4, 0.4, that's good. 3.2, 3.2, 3.2 for the inductances, that's all correct. Then we look over at the loads. 59.5 ohms, here we have 39.5 ohms, that's not the same. And here we have 19.5 ohms, that's not the same. You can keep on looking, but that by itself is sufficient to tell you this is not a balanced circuit right there, but you can continue looking. 76 ohms for the inductor, J26 ohms and J11 ohms. So